Welcome to Quantum Mechanics 1, an introduction. In this first series of lectures, we cover basic aspects of quantum mechanics, such as why there are intrinsic probabilities for quantum events and how we get them from the quantum formalism, how we describe quantum systems, and how we deal with their physical properties. These lectures are accessible to everyone with a good understanding of high school math. Enjoy! We look at a basic situation, a simple optical experiment, where we have a lamp, and the light emitted by the lamp is probed by what we call a polarizing beam splitter, PBS, and that has two output ports, plus and minus. And these plus and minus, they're just labels, but let's see what they mean. The lamp emits light that is vertically polarized, as indicated by this arrow. And the polarizing beam splitter is set such that the plus direction, that refers to probing light with this vertical polarization. And then the horizontal polarization is that goes to the minus output port. Now, since the lamp emits the vertically polarized light, and the vertically polarized light goes to the plus output port, horizontally polarized light would go to the minus output port of the polarizing beam splitter. If that's the situation, then we get 100% of the intensity as the plus side and no intensity at all at the minus side. Now, the polarizing beam splitter can be rotated, and we can rotate it by 90 degrees such that now the plus direction is horizontally polarized and the minus direction is vertically polarized. So now we have no intensity at the plus output port, and we have all the intensity at the minus output port. But that's not all that we can do. We can also set the polarizing beam splitter at an angle alpha, by which I mean that the plus direction that is probed is under an angle alpha of the vertical direction, and then the minus port is perpendicular to that. The polarization for the minus port is perpendicular to that. If we do the experiment like this, so we set the polarizing beam splitter at an angle alpha, then the fraction of the intensity that goes to the plus side is cosine alpha squared, and the fraction of the intensity that goes to the minus side is sine alpha squared. So here we had all of the intensity at plus, no intensity at minus, all of the intensity at minus, no intensity at plus, some intensity at plus, some intensity at minus, according to this fraction of cosine alpha squared and sine alpha squared. And this is a very, very well established fact. It's known as the Malus law in optics. So there's no doubt about this. You can easily do this experiment. You have your lamp, you emit polarized light, you probe it with a polarizing beam splitter, you turn your polarizing beam splitter to probe different values of alpha, and you find that the intensities are split in accordance with the Malus law. Now that's all about light as emitted from the lamp. But we know that the light is made up of photons. Now what does an individual photon do? An individual photon is either detected here or there. It does not split in two. However, the Malus law has to be true, even if we think of the light as making up of photons. And that means that for the photons that are emitted by the lamp and the polarizing beam splitter set at the angle alpha, some photons go to the plus side, some photons go to the minus side, such that the Malus law is correctly observed. That means that for the next photon to be emitted by the lamp, the probability that we will see it at the plus side is cosine alpha squared, and the probability that we will see it at the minus sign is sine alpha squared. These probabilities are the same for all photons, and as a consequence then, the fraction cosine alpha squared of the photons will be observed at the plus port, and the fraction sine alpha squared will be observed at the minus port. Now, these probabilities are correct, and they can be verified by an experiment. That's just the same experiment that verifies that the Malus law is correct. And these probabilities is what quantum mechanics tells us about the photons. Quantum mechanics does not make any statement about the fate of the next photon, whether the next photon goes to the plus side or the minus side. The only thing that quantum mechanics predicts, the only thing quantum mechanics can predict, are these probabilities of cosine alpha squared and sine alpha squared. Well, but maybe we are missing something. Maybe there is a hidden way in which the lamp instructs each photon to go to the plus output port or the minus output port, such that it looks to us as if there are these probabilities cosine alpha squared and sine alpha squared. Although, in fact, in a hidden way, for each single photon that is emitted, there is a deterministic decision whether it goes to the plus side or the minus side. So let's fantasize about this and imagine that there is a hidden mechanism which we symbolize by this hidden parameter lambda. We don't know what it is, but we assume that it exists, and it implements a set of instructions to the photons. It implements a mechanism that makes it clear for each photon to where it goes. So to us, this looks like a probabilistic phenomenon, but at a more profound understanding, in the sense of this hidden mechanism, there is determinism. And for each photon, it is clear at the time when the photon leaves the lamp whether it will go to the plus side or the minus side at the polarizing beam splitter. So we imagine that there is a function that kind of summarizes these instructions, which has the value +1 for some photons and the value -1 for other photons, such that the Malus law is correctly reproduced. One such function, there are many, one such function could have lambda between 0 and 1. And let's just, as part of the model, take for granted that the lambda values are uniformly distributed between 0 and 1. So for the next photon that comes, there is a lambda value. It could be anywhere between 0 and 1 with no preference for a particular region in this interval. And then this function is such, for example, that between 0 and sine alpha squared, so for this part of the 0 to 1 interval, the value of the function is -1, meaning that if this is the value for the particular photon, this photon is told to go to the minus output port. And for the remaining stretch between 0 and 1, that covers cosine alpha squared, the value of the function is +1. So if this is the function that we symbolize by a of lambda and alpha, then for the next photon that is emitted, perhaps it has its lambda values here. If that's the case, and that will happen for a fraction of cosine alpha squared of the photons, if that's the case, then the value of this function is +1, and the photon is told to go to the plus output port. The next photon that comes may have a lambda value here. Now here, the function has the value -1, so this photon is instructed to go to the minus output port. We do this for very many photons, and as a result, some photons will go to the minus output port, the fraction sine alpha squared. Some photons will go to the plus output port, the fraction cosine alpha squared. And the data that we collect, they will be perfectly consistent with the Malus law. So now we have cooked up a mechanism of a hidden kind that is deterministic for every single photon and produces the outcomes of the Malus law. It looks as if something probabilistic is going on with probabilities cosine alpha squared and sine alpha squared, But that's just the appearance if we are not aware of what this hidden parameter does. So, is this a different way of looking at things? Is this a valid way of looking at things? Is this a way that goes a way of looking at things that goes beyond just reproducing the simple situation of this experiment that probes the Malus law? The answer is no. And we will see why. For that, for understanding why these hidden parameters do not work in more complicated situations, it's enough to consider a situation that just involves two photons, photon pairs. So we have a source of photon pairs. For each pair, one of the photons is sent to the left, where it is probed by a polarizing beam splitter set at an angle alpha with its outputs plus and minus. The other photon is sent to the right, where it is probed by another polarizing beam splitter set at an angle beta, again with outputs plus and minus. So this by itself is like that experiment, this by itself is like that experiment, but now we have two such experiments going on at the same time with photons that come from a source in pairs. Now for each pair we now have such a variable lambda, so assuming that there is such a mechanism, and we have a function a lambda alpha of this kind that makes sure that the Malus law is observed on the left, and another function of this kind and make sure that the Malus law is observed for the photon that is probed on the right. These functions don't have to be the same, so this is why I'm using a lambda alpha on the left and b lambda beta on the right. But of course, just like the a of lambda and alpha takes on values plus and minus, the b lambda beta takes on values plus and minus 1. What is important here is that we have no dependence on the angle beta on the left and no dependence on the angle alpha on the right. And why is that? Well, the photons are sent to different experimental stations. In one lab we examine this photon, in another lab we examine this photons. There's an experimenter in this lab, there's another experimenter in this lab. This experimenter chooses alpha according to her free will. This experimenter chooses beta according to his free will. So now the free will of this experimenter and the free will of this experimenter, they are just independent things. And the choices for alpha and beta can be made so late in the game that there's not enough time for these devices to communicate with each other through some dark channel. So one could fantasize about having some communication between those, which is also hidden to us, but we just make sure that the decision about alpha and beta is made locally and very late, such that there's not enough time for communication between here and there. The point is that it will be sufficient to consider that what happens here depends only on the choice of alpha, and what happens here only depends on the choice of beta. So that there is an acknowledgement of locality here. What happens in this lab is local to this lab. What happens to this lab is local to that lab. And you can invoke the experimenter's free will to make clear that this is reasonable. So now let's look at what is observed. So for one photon pair, we could have outcome plus on the left and also outcome plus on the right. So plus and plus. Or we could have minus on the left and minus on the right. Minus here, minus there. These are possible outcomes for the pairs. We can also have plus on the left, minus on the right, or minus on the left, plus on the right. The first two instances have the same outcome on the left and the right, so we call this positively correlated and assign the number +1 to these events. When we have plus on one side, minus on the other side, we have a negative correlation and we call that -1. And now we do this very often and then we average over these results, and that gives us a correlation function, a correlation that depends on the settings alpha and beta, and that is simply the number of positively correlated events minus the number of negatively correlated events divided by their sum. So we divide by the sum for normalization, and that makes clear that if all of the events are positively correlated, so we don't have negative -1 counts at all, then this correlation function will be equal to +1 if we have only positively correlated events. If we have only negatively correlated events, then the value will be -1. For the more general situation, it's a number between +1 and -1. We will have some +1 events, we will have some -1 pair events, and dividing by the sum will give us an average value of this plus and minus, which is somewhere between -1 and +1. So now let's see how we get this number from these ingredients, the A lambda alpha and the B lambda beta. Well, the values that we see here, well, these are just the products of the A value and the B value. So A equals +1, B equals +1, the product is +1. A equals -1, B equals -1, the product is +1. And here one of them has the value +1 and the other one has the value -1. So again, this is just the product of the values that these functions take on, one on this side and one on this side. So this correlation C alpha beta is just the average of all of those numbers. Sometimes this product is +1, sometimes the product is -1, and we have to average over all the lambdas. So we have the product A lambda alpha, B lambda beta. There is a distribution of lambda values which are symbolized by that, and there's an averaging over all of this, which is an integration over the lambda values. And so this is the expression from C alpha beta as we calculate it from these hidden functions A lambda of alpha and B lambda of beta. So here we have the expression for the C alpha beta, and it comes from the data observed in the experiment. How often do we see positive correlations? How often do we see negative correlations? This is the way how we calculate this number from an underlying theoretical description that assumes these hidden parameters. So let's now see what we can conclude from the assumptions that there is such a mechanism described by these functions A lambda alpha and B lambda beta of the kind that we just discussed. We are here aiming at an argument that was put forward by John Stuart Bell in 1964. And it considers not just one such correlation, but a combination of 4, where we have settings alpha and beta combined with settings alpha prime and beta prime in the following way. So there is the correlation for alpha and beta, the correlation for alpha and beta prime, the correlation for alpha prime beta, and the correlation of alpha prime and beta prime. So we have 2 settings on this side with alpha and alpha prime, and 2 settings on that side with beta and beta prime. We add 3 of the correlations, we subtract 1. Now we are writing what is this number that we get by expressing it in this form, which tells us that we have an integral over all the lambda parameters. Now we have 4 terms. Okay, so there is A lambda for alpha and B lambda for beta. And then we add to that the term which has A lambda alpha and B lambda beta prime. I do this by adding the b lambda beta prime to the b lambda of beta, and then the sum is multiplied with the a lambda alpha. So these two terms are these two terms. And then we repeat, but now with alpha prime and beta prime, with the two b's subtracted rather than added. And so altogether, we have this combination of a lambda alpha terms and b lambda beta terms. Now, let's remember that each of those numbers, a, b, wherever they appear, each one of them is plus or minus 1. So for the two b's that appear here, for beta and beta prime, and the common lambda, either these two numbers are the same, in which case this sum is plus 2 or minus 2, multiplied with the a, which is plus or minus 1. The whole product is plus 2 or minus 2. When the two b's are the same, plus 2 or minus 2. But in this case, over here, we subtract the two b's, and that's the same value twice. So we get 0 for this combination. Now the other possibility is that one of the b's is plus 1 and the other one is minus 1. So they are different. When that happens, then rather than having plus minus 2 over here, we have 0. And over here, for this combination, we now get plus or minus 2. Which is to say that this whole expression here is equal to plus 2 or minus 2 for each value of lambda. And what we then calculate here is an average of numbers. Every single number is between plus 2 and minus 2. So then, of course, also the average value will be between plus 2 and minus 2. It then follows that this combination that we are looking at cannot exceed 2 in magnitude. So, what I'm now summarizing is that the absolute value of the expression that we began with can never be larger than 2. And this statement is the so-called Bell inequality. Now, it looks very plausible as it was derived. After all, we are not making any strong assumptions except that there is a mechanism of a quite general art that gives us these expressions for the correlations. Now, what about the data of actual experiments? Well, such experiments can be conducted, and if we take the data and calculate the correlations, sometimes we find values which are really larger than 2. Quantum mechanics, as we will see in a later lecture in this cycle, allows values as large as square root 8. And that's a little bit more than 2.8. So clearly above 2. And many experiments by now have been conducted where numbers for these correlations found that clearly are violating Bell's inequality. In fact, this year's Nobel Prize in Physics, 2022, has been awarded to 3 people who conducted the pioneering experiments of this kind. John Clauser, Alain Aspect, and Anton Zeilinger. Now, what's the lesson that we are learning from all of that? Well, clearly, the reasoning that established Bell's inequality has to be refuted. There is no such mechanism. We have to accept the fact that the random events that we observe in these quantum experiments are randomly realized. There is no mechanism that determines which detector will click for the next photon pair that is emitted. This is a brutal fact of life. We have to learn to live with it. And in a very profound sense, quantum mechanics is about learning to live with this fact. In summary, we have the source that emits the vertically polarized photons, which we probe by measuring polarization under an angle alpha, which gives us two outcomes that we labeled with plus and minus. So for each value of alpha, which is a continuous variable, we have two outcomes, two discrete outcomes. And it's the marriage of this continuous feature and the discrete feature that forces us to consider probabilistic predictions for these kind of experiments. Now we could wonder whether these probabilities are just an indication of a lack of understanding. Perhaps there is a hidden mechanism that determines what the next photon does, but we don't know the mechanism, and therefore we are just guessing, and this is where the probabilities enter. If we follow this line of thought, we end up with the Bell inequality. And the Bell inequality, as we know, is violated by the actual data from real-life experiments. So we are led to the conclusion that there is no such hidden mechanism that is deterministic, and the lack of knowledge about the mechanism forces us to make probabilistic determination. No, there is no mechanism. We know this for sure. Now, putting all of this together, in particular, the union of the continuous and the discrete, gives us the formalism of quantum mechanics, which is the useful machinery to talk about physics at the atomic level. And that necessarily leads to probabilistic laws of physics. This is a brutal fact of life, and we have to learn to live with it.